Okay, good afternoon, everyone. Um, so, today's lecture is going to continue our discussion of, superfluidity and its connection to broken symmetry. So let me just quickly summarize the topics we covered yesterday on Monday. So the fundamental property of both the Bose gas and the electron superconductor is off-diagonal long-range order. And in the Bose gas, this is characterized by this long-range correlation function between the, you annihilate a boson, say at a point 0, and then you put it back in at point R or vice versa. And because there's a Bose condensate which has a rigid phase, there's a memory of the phase of the boson wave function, and therefore this thing has a non-zero limit as R goes to infinity. And that fundamental characterization is also true for the electron superconductor, where now instead of the Bose annihilation operator, we have the Cooper pair operator, which annihilates a pair of fermions a distance little r apart with spin up and down. And the amplitude for that is some Cooper pair wave function g of r. Okay, so this operator is Bose in quotes. It's Bose in the sense that if you separate the center of mass coordinate capital R far enough, capital R can go to infinity because it's large as the size of the sample. So you can easily separate Cooper pairs no matter how big they are on the microscopic scale, where the capital R's are really far apart. Then these operators commute. But they're not really bosons in the sense there's no elementary boson here. It's really made up of a pair of fermions which quite easily unbind from each other. Okay, so just to keep that in mind, when we talk of this function g of r, it's a function of the relative coordinate, whereas this capital R is a function of the center of mass coordinate. In fact, all our discussion today will be about the center of mass coordinate R, but I will, with the use of notation, write it as small r. But just keep in mind, when we talk about the boson field or the phase of the boson in the Cooper pair context, we're talking about the center of mass coordinates of the electrons. Well, what BCS theory tells us is something very different from what happened to the center of mass, other than it has perfect long-range order. Excuse me. It tells us that the relative coordinate g of r is exponential decay. And this exponential decay is characterized by a length called the coherence length. So let me put a COH here so that this is not confused with the other lengths we'll talk about in the center of mass coordinate today, and also talked a little bit about it yesterday. So this coherence length goes as we have Fermi velocity divided by the parameter delta, and the big achievement of BCS theory was to compute this delta. So it's related to some attractive interaction, which I won't review right now. And in addition to determining the coherence length and this decay of the relative wave function, it also determines the spectrum of fermionic energies in this way. All right, so any questions on that? Okay, great. So as you're going to see eventually in this course, not today, this is actually, I kind of lied. This is actually not the most fundamental characterization of superfluidity. And in two dimensions in particular, the right-hand side of both of these in a strictly 2D film of bosons or electrons, which are easy to get these days, this is actually 0, even though you're still in a superconductor. So the more fundamental characterization is what we're discussing, and that has to do with the nature of the broken symmetry. So I won't go over what we talked about for the Ising model, which has a surface tension. So here we imagine we're talking about a Bose gas, but I equally well could be talking about Cooper pairs. So when I'm talking about the little r coordinate, I'm referred to the center of mass coordinate of the Cooper pair. So there's some condensate. Well, there may or may not be a condensate, but what you do is you take your superconductor or superfluid and conduct it and couple it weakly to some reservoir. And there are two reservoirs, one on the left and one on the right. And the reservoirs are a source of perfect bosons with perfect phase coherence. So on the left reservoir, there's some field eta L, which is the amplitude, in this case, for creating a boson with this factor eta L on the left. And similarly on the right, there's a factor eta R for creating a boson on the right. So now we ask what happens if the eta left and eta right have different phase factors. So if the whole thing was a coherent superconductor, that is, you had both. Here's your sample. Here's the left reservoir and the right reservoir. Here's your Bose gas. And this is some kind of weak coupling between them. If the whole thing came to a ground state, the Bose condensate will be everywhere and have the same phase. But what we want to do is, if this boson has some angle theta, say it's pointing here, then on the right-hand side, you want the boson, the phase of the boson, to have a different phase theta. And how exactly you can change the phase is something, well, we'll talk, you'll see a little bit how you can change the phase today. But suppose you're able to, this as it's a Gedanken experiment, suppose you're able to change the phase of the wave function of this Bose condensate on the left and the right. Then we can ask how much energy does it cost to twist the phase in this way? I guess we called it delta theta here. So the change in free energy from no twist to twist is the quantity we want to compute. And we argued that what's going to happen is that the twist will be uniformly spread out. And it makes sense, just like the shear strain in a solid, the energy per unit volume will be proportional to to the gradient squared of the phase. And so you get this expression here. Let's see. Yeah, okay. So the gradient here, grad theta, is theta over L, which is the twist. So this, to keep the notation consistent, there should be delta theta here. Delta theta, delta. Okay. That capital delta has nothing to do with the superconducting pairing gap. Sorry about that. Okay, so the gradient is delta theta over L. So the energy is proportional to that whole thing squared times the volume, and the volume is A times L. And then the coefficient is the most fundamental quantity we'll talk about today. Well, and a few other related quantities. Rho sub S, which we'll call the helicity modulus or the superfluid stiffness. Depending on physical context, one or the other might make sense. So let's just call it superfluid stiffness for this lecture. Sometimes it's called the superfluid density, but that's really a misnomer because it's not even a density. It doesn't even have the units of density. Okay, it has the units, as you can see from here, of energy times length to the 2 minus d. Because delta theta, the twist, is always a dimensionless number. Okay. And we are, and the reasoning for this, which I've already said in words, is that the energy density cost is the local phase gradient squared. Okay. All right, questions? Okay, so now we want to have a picture of a superfluid in the case. We forget about this definition for now, just briefly. And we want to imagine we have our system sitting there and the post condensate is not uniform. It's not uniform, could be non-uniform for a variety of reasons. You perturbed it a while back, you kicked it, there are thermal fluctuations, whatever. So We want to talk about a system where the condensate is varying from point to point in space. Now, if you really want to do the calculation correctly, you would have to go back to, say, the BCS theory or the Bogoliubov theory and allow for the condensate to be space dependent and redo everything. Now, that's too complicated. It requires you to go to a computer for every question you ask. But our hope is that there's some analytic progress we can make in the limit where this spatial variation is slow on the scale of the coherence length for the BCS superconductor, and there are similar length scales like the de Broglie wavelength for a BEC. So we want something that varies slowly. So how do we characterize this slowly spatially varying, and even we'll only consider time variations, spatial variations for now, but the same logic also applies to time variations. So let's imagine some spatial variation. How do we characterize the spatial variation? Well, the idea we have is that given this, Mexican hat potential, the most of the variations will happen along the angular direction. Anything along the radial direction would quickly come to equilibrium because it costs a lot of energy. So we can conclude that to describe the properties of superfluid or this condensate with slow spatial variations, we need what you call an autoparameter, a phase superfluid phase field theta of r. And for now, we just forget the fact that theta has to be periodic. That will come back to haunt us very quickly. But for now, just imagine that we can identify theta everywhere, and it doesn't get close to 2 pi anywhere. Well, at least the variations never are close to 2 pi. So this tells us, when we're doing the thermodynamics of a superfluid, when you learn classical mechanics and theory of the ideal gas, what you learn is that, well, you don't have to keep track of the velocity and momentum of every particle. All you need is the pressure and the temperature and the chemical potential, and then you can write everything down in terms of that. So for what we concluded for a superfluid, yeah, we need those quantities too. We need the pressure and the temperature, but we need something else. So there's another autoparameter or thermodynamic variable that we have to introduce, which was not present in in thermodynamics until superfluids were understood. And that thermodynamic variable, much like the pressure, can vary slowly with position and time, and that's the phase theta. So now so that's step one. Now we need some kind of equation of state for this thing, which tells us how does the energy of the system, the free energy at finite temperature or the energy at zero temperature, vary with theta. Well, that's exactly what this definition tells us here. It just, we assumed here that the energy would be rho s times the gradient of theta squared. So we conclude that for slow variations, the number rho s that appears here, which we can measure in this twisted boundary condition experiment, is exactly the number that's going to appear here. So there it is. This is our theory of a superfluid with spatial variation with the coefficient rho sub s. And at long wavelengths in the superfluid phase, you have to add this term and allow for this new classical thermodynamic variable phase theta in your description of its response to external perturbations and so on. Okay, so that's just a quick summary of how you go from a very quantum phenomenon, which is Bose-Einstein condensation, to what's called an effective classical description in terms of just a new thermodynamic variable, theta. And at this point, this theta, the fact that it's a quantum variable is not that crucial for anything so far. It becomes crucial once you remember that theta has to be periodic in 2 pi. And that's something we'll probably come to in the next lecture. But for now, let's not worry about that issue. Okay, so questions? Everyone happy with that? So this is our new theory for a spatially varying superfluid.
May I?
Yes.
Question. Conceptual, very basic.
Yes, go ahead, Joanne.
About the theta, there's no absolute value of a theta with this one, but just the difference, right?
Yeah. I mean, you have to define it with reference to some other superconductor, but in terms of the boundary, yeah, but it's only differences in theta that make correct.
I don't know whether it's a good timing to ask this, but I always forget how the Martin sphere line will explain when he showed us superfluidity vortices. I think the phase not be really major, but he has a nice figure, like, you know, it's like some kind of a vortex.
And yeah, so the pictures, we're coming to that in a minute. What he's showing the pictures are the supercurrents, which depends on the gradient of the phase.
Right. So I suppose only what you can really show is like the winding, like +1, -1, that makes the difference. But the phase.
Okay, I don't want to.
Oh yeah, sorry.
I want to keep a discussion of vortices for. We're coming. That's next lecture, I think. All right, but for now, let's ask a more basic question. How do we measure ρs? What is the consequence of having a non-zero ρs? And what I want to show you is that, you know, this looks like a very innocuous little Hamiltonian. But once we have this, then using this and gauge invariance, we can prove that this thing is a superconductor and displays the Meissner effect. Okay, so how do we show that? Well, the key missing ingredient so far is gauge invariance. So now we have to introduce the electromagnetic field. And we can ask, okay, now you've got this effective theory. Now let me add a very slowly varying magnetic field for now. Let's just say a vector potential A. And I'm going to work in a gauge where everything is time independent. So I have some, well, no, you can make A time dependent too, but for now, well, let's just make it time independent as written here. Okay, so now we have to ask what happens to this effective action where you have no idea what this number is in the presence of a vector potential. All right, so this is what's given by gauge invariance. So if I had suppose I consider bosons of charge, charge Q for now. Then in the presence of a vector potential, I know the underlying microscopic Hamiltonian of the bosons has this so-called minimal substitution. We replace the gradient by minus IQ over H bar C times A. And I apologize, these notes are in CGS units. And there's also going to be some ugly factors of 4 pi that appear as a consequence in a minute. So, okay, at least for this equation, there's no, you just drop the C if you want to go to MKS units or the SI units. All right, so this fundamental property of this Hamiltonian and is gauge invariance, as you know. That is, you make a transformation to the field operator by this factor e to the IQ over H bar C and A by grad chi. And now you notice that theta, the angle of the Bose field, transforms by exactly this factor here, which is Q over H bar C. All right, so this is just, you know, because psi is the phase of the Bose operator. So this is for bosons, and how about for Cooper pairs? Well, it's easy to see that for Cooper pairs, you know, this Q will be exactly 2E. And why is that? And that's an exact result. There's just no, you know, even though I don't know so much about what the wave function of the Cooper pairs is, what I know for sure, going back to this definition right here, if I did this for electrons, here, that it's made up of two electrons. And here I'm imagining that, you know, I'm talking about transformation as a function of R. So where little r is some very short distance, and I'm looking only at phenomena scales much larger than the coherence length C coherence. So in that case, each one of these electrons will also pick up a factor of e to the I chi over h bar, because each carry charge 1 under gauge transformations, and therefore psi c of r will transform with 2 electron operators. Okay, so in the limit where I can get rid of the short distance relative coordinates of the 2 electrons within a Cooper pair, that's always, at the most, it's a few thousand angstroms. In the high TC superconductors, only 10 angstroms. And we are now talking about phenomena on the scale of centimeters. So in that case, the Cooper pair just behaves just like a charge with charge 2e. So theta, therefore, is not gauge invariant. Not only Juven, not only is the constant part of theta not defined, it's not even gauge invariant. So how do we make it gauge invariant? But the free energy must be gauge invariant. Well, there's only one choice. The only way to make this action gauge invariant is to put in this little a. So this is a very powerful argument telling us what happens, what is the energy cost of a magnetic field in a superfluid. It's given by this. Okay. And now you can already see something rather remarkable. Suppose I have a uniform superfluid and I just put a magnetic field on. But what I seem to be finding that the energy goes as a squared. If gradient theta is not present, the energy goes as a squared, not b squared. In normal space, energy goes as b squared. A is b cross r. So when you integrate it over volume, it's much larger. So putting a magnetic field inside a superconductor costs a huge amount of energy, and the superconductor will do everything it can to get rid of it, and that's the Meissner effect. So you see right away, and if you were thinking about time-dependent phenomena, this would be the mass of the photon, but we're not talking about that right now. Okay. All right, so this is a bit inconvenient to work with, but it's the proper gauge invariant form. But let's just simplify things for us now and work in the gauge where del dot A is 0. The full gauge invariant theory will require time dependence and time-dependent gauge transformation. There's no need to get into that for now. Okay, well then, as long as this is the case, we can just expand this out. It just becomes the sum of 2 terms. And there's this term, which goes as a squared. And then what is the current? So now you apply this is some source field that you applied, but from quantum mechanics, for any Hamiltonian, the current is just the derivative of the energy with respect to the vector potential. This is something you can verify just by starting with this microscopic Hamiltonian and just computing for the microscopic Hamiltonian, dH dA, and you'll get, in terms of the microscopic fields, these are the microscopic boson fields here, not the super pair in this case. You'll get the usual expression that psi dagger psi I minus psi grad psi dagger, or 2mi or something like that. Okay, so we can use that and get an expression for J, this dH dA, and this is just equal to the vector potential. So this is the famous equation, the so-called London equation, which is really the key to superfluidity. That in this gauge, del dot A equals 0, this is true. I mean, you can see that this is, A is not gauge invariant on the right, so this is not the proper gauge invariant form of it. I think maybe next lecture, or maybe, yeah, we'll see a more gauge invariant version of it when we do the Ginzburg-Landau theory. And you can see, the London gauge is kind of important because this tells us now that del dot J is del dot A. Here, Q is not a wave vector, it's just a charge, which is 2 so del dot A equals 0 implies del dot J equals 0, so current is conserved. So that's good. That's why we definitely need this gauge choice for this to make sense. This expression, however, is fully gauged true in any gauge. This one here. Even with time variations, it's still correct. Okay, so that's the famous London equation, and it immediately has a lot of remarkable consequences. So what you see is the London equation has only this famous superfluid stiffness here, rho sub s, 2 h bar c, just fundamental constants as we know. So the only thing we need for the London equation is the superfluid density. All right, so what is the implication of London equations? Well, first of all, you can take the time derivative of the left and the right-hand side. And now this is just the electric field. So now we see that dj dt is rho s q squared over h squared times E. So this is not like Ohm's law. You know, Ohm's law would be J is sigma E. Which is J is sigma E. So this, if you take the Fourier transform of this, this implies that sigma is something like 1 over I omega. It diverges, is practically infinite. So this is telling you that this is just Newton's laws in a way, that if you apply an electric field, the condensate will accelerate. So basically, if you want a constant current, you better not have any electric field, meaning that you can drive a current without any field, meaning there's no voltage difference, meaning there's no resistance. So just the fact that rho s is non-zero tells you this is a superconductor. In fact, it's a very general argument. You can put in impurities, you can put in all kinds of disorder, whatever. You don't even need translation invariance. This pretty much tells you as long as rho s is non-zero, you're going to be able to draw a current without any electric field. Okay. So that's marvelous, and it also tells you what this coefficient is. It's related to rho s. Okay, everything, the only one number we need to know to characterize the superfluid is rho s, all its long distance properties. And then the Meissner effect. So now imagine A doesn't produce is not time dependent, but time independent and has a magnetic field. So del cross A is B. All right, and I'm sorry here again, I apologize. I'm using the CGS units. Should rewrite these notes in SI units. So CGS units, curl B is 4 pi over C times J. So curl of B is 4 pi over C curl of J, but J is related to A, and curl of A is B itself. So therefore, and del dot B is 0. So now I can simplify this equation using Maxwell's equation. I get an equation for B. So this is the, I don't know whose equation this is. Maybe it's just a consequence of London's equation. So may as well call it another London equation. So now I have this equation for a B field inside a superconductor. It's that the Laplacian squared, after using here, we just use the fact that del dot B is 0, no monopoles. And then I get this equation that the Laplacian squared of B is 1 over lambda L squared. So lambda L is then a length, because just dimensionally it has to be a length. And it's related to rho sub s by this famous formula then. So once you, so there's a length that I can measure called the London penetration depth, lambda L. And this, typical superconductor would be also a few thousand angstroms. The London penetration depth is related to rho sub s, and then fundamental constants of nature. This is just 4 Planck's constant velocity, and if you've got all the units right, CGS or MKS units, you'll find that this thing is precisely a length. Okay. So this is the expression for London penetration depth in CGS units. I think there'll be some mu naughts floating around if you did MKS units. So this is why physicists don't like MKS units, at least theoretical physicists, because this mu naught is a very annoying thing to keep track of. All right, so what's the consequence of the London equation? Whoops, what happened there? Oh, yeah, okay, there we are. So consider the following. We're just going to solve this equation with this boundary condition. So you have some B naught in vacuum. So here's our superconductor. This is the boundary between a superconductor and vacuum. You put B equals B naught here, and then you want to figure out what happens inside the superconductor. Well, you just solve this equation. This is a very simple equation, just a second order equation, and the solution, of course, is just a pure exponential. The B field will decay inside the superconductor to 0. So it'll become weaker and weaker and weaker in a distance of order lambda L. And why does this B field become weaker? So you just put you have a superconductor sitting there. You turn on a B field, leave it on, and then the B field get expelled from inside the superconductor, and that's a stable situation. It will sit there forever. And why is B field 0 inside? Well, you can go back here and use Maxwell's equation. Curl of B is 4 pi over Cj. And what you'll find then is that there's a current, a supercurrent, say going into the board. So there's a supercurrent on the surface, which is just flowing on the surface forever, without dissipation. So if you put a magnetic field on next to a superconductor, there's a supercurrent on the surface going this way into the board, into the screen, and that basically has the effect of the B field going to 0 inside it. So once you're in the bulk of the superconductor, over a few thousand angstroms in, B is just 0 down here. And that's the famous Meissner effect. So this is really the more fundamental property of a superconductor, that it expels magnetic fields. And as you can see, it's a direct consequence of having this stiffness. Once you have the stiffness, then you have the A squared term, and that causes all kinds of problems. That changes the whole physics of everything. Now, there's similar arguments for neutral superfluids of how they can transfer momentum without dissipation. Those are a bit more complicated, but they're very, very similar. Instead of the vector potential, you have to do a Galilean boost and things like that. So I won't go through that. In the homework, there's one problem where you investigate some arguments of that type. The gauge invariance arguments are much more familiar to physicists, and also for superconductors, that's sufficient. Okay, questions?
Sorry, I have a clarification question about this effective Hamiltonian.
Yes.
Like, are we getting this by making some approximation on the Bosonic Hamiltonian that you wrote down before this, or like, what is this Hamiltonian?
It's a postulate for the low energy physics, thermodynamics of a superfluid. It's a fairly ironclad argument. But what we haven't done is actually computed what rho sub s is. So So, and that's in fact precisely the next slide. How do you compute this quantity? So ultimately, if you knew everything, you tell me a Hamiltonian, I should tell you what rho s is. You tell me a microscopic Hamiltonian of your system, I should go back and compute what rho s is. That is not an easy task. And we can only do it in certain limits. But nevertheless, I can say that, well, I can't compute your Hamiltonian, but I can do an experiment. I can go in and do the experiment and measure the London penetration depth, and from the experiment, therefore, I can tell you what the value of rho sub s is in your effective Hamiltonian. Okay, but of course, yeah. So that's kind of what I've just related rho sub s to the London penetration depth.
So like it depends on the interaction U that you wrote down.
Yes, and it will, but computing that requires, this is where Feynman diagrams come in. You have to do a calculation, and this, since I'm trying to avoid Feynman diagrams as much as I can in this course, I thought that's 295B, right?
Okay, thanks.
That's, in fact, yeah, so here's how do we compute rho s? So that was the next slide here. So again, let's just take a microscopic theory now. And the way we're going to compute it, is not by computing an effective Hamiltonian. This is the kind of trick you often play. Because I said, this was a postulate. This Hamiltonian was a postulate here. This was a postulate. But then I combined that postulate with gauge invariance, which everyone believes in, to get this thing. And from this Hamiltonian and the definition of a current, I came up with London's equation. So now I can turn it around. I say, if I can show that my theory obeys this equation, then I can figure out the value of rho s. So that's what I'm going to do. I'm going to take my Bose system. I'm going to put it in a magnetic field and compute the current. So that's the kind of calculation called linear response that 295B is all about. I'll just do a baby version of it today. And from that calculation, if you carry it out to higher orders, you can compute rho s. So this is what, you don't actually compute the effective Hamiltonian, you do a simpler calculation where you try to see if this equation is valid. Yes, Joven. You raised your hand, or was that from a while back?
Yes, if I can. I think just a physical meaning for rho s, as you say, is superfluid stiffness of this helicity modulus. And
yes.
The physical meaning for that, as you write on the London equation, seems like the proportional to the superconductivity current, right?
Well, the proportionality, but the supercurrent can be anything. We don't know what the value of the supercurrent is.
So let me just say, I'm trying to compare physical picture. Larger the stiffness, larger the rho s. In the Hamiltonian form, it seems like the theta angle will be fluctuate smoother and slower, correct?
Correct.
Lower energy, right? So rho s stiff, more stiff, the angle, the physical picture, you think about the wave, fluctuate more smooth. Well, however, the current seems proportional to that. So that means that it's easier to conduct, easier to superconduct with the smaller stiffness, and when the theta angle fluctuates smoother. Is that
well, I think the correct way to think about it is that notice this thing: the larger the rho s, the smaller the lambda L.
That I also going to say yes.
So then when you put a magnetic field with a very high stiffness, the London penetration is very small. So the magnetic field go to zero right away, which means there's a huge supercurrent right on the surface. So yeah, you're right. The superfield current is large, but it's only on the surface, but over a much tinier region.
Okay. So this picture, this going inside a plane, this cross is which field? Just make sure what you're doing.
The cross is the current. The current is going into the board.
Okay. Right.
And the B field is the arrows. These are the B fields here. B of Z.
No problem. Another curve.
The current.
Yes. Two more things. One is that you promised we will discuss the microscopic understanding of superconductivity. Here you give a macroscopic, right? So maybe later at some point the microscopic.
No, we have already. Microscopic we've already done.
Yes, we have a ground state wave function, but maybe there should be some quantity.
We started with the BCS. We started with the BCS Hamiltonian. We have the BCS wave function. We have the energy gap. We have the spectrum of excitation. That's about as microscopic as it gets. The only question left is what is the origin of U naught? Right?
I suppose.
But at least for.
Should one compute something diverge? It's a really naive question. Certainly, I take course before. I wonder whether there should be some divergence quantity that one can compute from ground state wave functions. Is that something one will need to check in the?
Well, if you took the yes, there is. If you took the ground state wave function of a Fermi liquid and computed a certain propagator for the Kupfer-Pairs susceptibility, that has a divergence. I didn't do that, but okay. I just went directly into the superconducting state, which is totally stable and nothing is divergent in there. But the Fermi liquid is the part when it's unstable has some divergent responses. Okay.
Thank you.
All right. So thank you. Any other questions? Oh yeah, then more. Yeah, please go ahead. Neng Chun Chui. Sorry, I may not have pronounced your name properly. Please go ahead. Okay. No. Okay. Neng Chun. All right. Okay. So yeah. So as I was saying, how do I compute rho s? Well, what I'm going to do is I take my Bogoliubov theory and just add a vector potential and compute J. Well, to first order, that's very simple. Okay, so J would be this operator. And notice now J has two terms. When I take dH, dA, I get this. This is sometimes called the paramagnetic term, and I also get this term, which is called the diamagnetic term. So in the presence of A now, which is present in the Hamiltonian, I have to compute the value of J. So this is what's called a Kubo formula, and this is where diagram you now open up your textbook on diagrams and just turn the cranks and draw lots of diagrams to compute this. I'm going to avoid that because what happens is that I'm going to do the calculation to first order in the Bogoliubov theory for a Bose gas. Okay, so what did we say for a Bose gas? Okay, I haven't written this down here. Right. So we said what we had for a Bose gas was, we had psi. We had B0 expectation value was square root of N0, and BK were the excitations. Okay, so let's start from that state. So what happens for that? What that means is that psi of X is square root of N. And so that's a constant plus some fluctuation with son of X. This is coming from BK not equal to 0, from the Fourier transform of that. Okay, if you plug this expression in here, sorry, right. What am I doing here? Okay. Yeah. So into this. Into this expression in here. Well, what's going to happen is that this is 2 powers of psi, and this is only. However, the largest contribution to psi in the expression for the current is square root of N naught. But if I put psi equal to square root of N naught, this gives me 0. So as in the Bogoliubov theory, to expand to leading order in square root of N naught, the first term will have one of these psi's. The one without the gradient will become a square root of N naught. And the one with the gradient will become square root of psi 1. Okay. All right. Now notice that if I now take this expression for the current, the Hamiltonian has a term. The Hamiltonian is something like some H at A equals 0 plus A dot JP plus A squared, something like that, 1/2 A squared. So this A dot JP with the integrated over all space, when you just expand this out, you expand this term out. The first order term is just J dot A, where this is J. And now the point is that in the London gauge, if I integrate this over all space, it has only one gradient and nothing else, so I can integrate by parts, and when I integrate by parts, I get 0. So for del dot A equals in this London gauge, A dot JP is 0. So in this same gauge, if you want to compute the expectation value of JP, which you would compute by doing a perturbation theory in this term is just 0 to leading order. However, this term is not. So this tells us that the current is just comes from the A squared term, whereas Q squared over MC times rho, which is the total density. Okay. So that's another very important thing we conclude here. What appears here, now where did the rho come from? Well, that's just, yeah, okay. So what I should correctly say is that N naught, the strength of the condensate, the value of N naught, this quantity N naught here, simply doesn't appear in the coefficient between Q squared over MC and A. What is rho here? Okay, yeah, so rho, yeah, let's just go back and look at this. Sorry, I'm being a bit too glib here. So this term, the A squared term from here is D3R A squared times psi dagger psi. So when I just take the expectation value of this, there's a psi dagger psi here. This gives me a rho, which is the density, but it's the total density. So therefore, I can then compute the stiffness by the connection between the London equation and the superfluid stiffness. And this is really the key point of this whole calculation. This is the total density of bosons. Of Cooper pairs also. So you have a kind of remarkable result, which in a Galilean invariant system is exact. Right? You could imagine you have lots of interactions between the boson. In this case, we work to first order in the interactions. And those interactions are going to deplete the condensate that's present at 0 momentum. So the condensate gets depleted by interactions. As we saw, some of the bosons go to finite momentum. Amazingly, that depletion does not contribute to the stiffness. The stiffness is as if the whole system, both the bosons in the condensate and out of the condensate, are contributing to the stiffness, to leading order. And if you had Galilean invariance, you can prove this result is exact for a Bose gas. So that's kind of amazing. So if you have superfluid helium, which is a Galilean invariant system, in a tub, the condensate fraction, only 10% of the bosons are in the 0 momentum state. The condensate fraction is about 10%. But if you compute the superfluid density, or if you ask what is the number of bosons that contribute to momentum flow in the presence when you flow that thing, it's all of them. The superfluid density is the total density. So it's a much better superfluid than you would naively think. It's not the condensate itself that's contributing to superfluidity, it's the stiffness, and the stiffness comes from everything. Okay. And in fact, this is what becomes very important in 2 dimensions. In 2 dimensions, the condensate disappears. The condensate is 0. There's no off-diagonal Lagrange order, but the stiffness is still non-zero. And that was understood by Kosteles and Thouless. And we will talk about that in a few weeks in great detail. Okay, so we've covered a lot of ground, and these are very deep results that took the community many, many years to understand. And hopefully you got the spirit of the arguments. They're really ultimately, very simple arguments based upon, as we saw, gauge invariance and some kind of understanding that there is a new classical variable called the phase in a superconductor or a superfluid. Once you accept those 2 facts, you can pretty much derive all of this. Questions? Sorry, I think let me just quickly review this calculation. So what you do is you expand this to order A squared. So you get two terms. You get a term that's A dot J, A dot this, and then you get A squared with a factor of 1/2 times psi dagger psi. And then when you expand this term to first order in the condensate, so that, or the part above the condensate to first order in psi1, you find that this term is just 0. Its expectation value of 0 because it only doesn't contribute to the Hamiltonian at all. So the only term is this term left over, the A squared term. But the coefficient of the A squared term is the full psi dagger psi. You know, this thing psi dagger psi is n naught plus psi dagger 1, psi dagger 1. It has nothing to do with off diagonal long range order directly. It's just that, the total density. And that's why it's the total density of the bosons that appears in the superfluid density, not the condensate fraction squared. Not the density times the condensate fraction, as you might naively think. And many people do that even in papers and seminars to this day, but it's not true. Okay, so, all right. Yeah, so the basic idea of, this is the physical picture London had. There's some rigidity to the wave function, and here the rigidity is that phase gradients cost energy. If phase gradient cost energy, the wave, then what happens is that when you apply a magnet, in a vector potential A with del dot A equal to 0, basically you don't pick up any phase gradients, and the current is just equal to the bare current that you would expect from the A squared term. Okay, that's not a very not a very precise way of stating it, but okay, this gives you some gut feeling for what's going on. Questions?
Excuse me.
Yes, Julian.
Can I? So you are trying to emphasize the superfluid stiffness rho s. Some people in the seminar like to write proportional to the density square. I made a mistake. Did you try to?
No, sorry. No, sometimes you might think very naively that rho s is proportional to n naught. So, you have some condensate, and then density of particles in the condensate is n naught. So you might think that rho s is proportional to n naught. Don't think that. That's not true. Rho s is proportional to rho. So rho here is n naught plus even the bosons outside the condensate. To first order in U naught, there's no correction, and then at higher orders there can be corrections, and in a superconductor there are corrections because you don't have Galilean invariance. For this to be exact to all orders, then you need some symmetry, which is present in something like superfluid helium-4, or also in ultra-cold atomic gases. I mean, the potential is very shallow, the trapping potential, so it's a good approximation to imagine you do have Galilean invariance locally. Yes, Patrick.
Does the confusion where people think that rho s proportional n naught come from like doing perturbation theory to first order in psi1?
Well, that's what I just did, but that's exactly what I did carefully. And when you do it carefully to first order in psi1, we found that the psi1 contribution, so we make this decomposition, we put it in here, and then we find that psi1 doesn't contribute at all to the current.
I see what you mean, but like if you look down, if you go down where it says that rho s is n naught plus psi dagger 1, psi1 dagger plus psi1, in first order perturbation theory in psi1, the second term goes away. So it seems like
first order perturbation theory U naught, it doesn't go away. It's definitely there. We computed this psi dagger. Yeah, we computed this quantity.
Excuse me, sorry. The equation.
So let me finish, Juan, once again. So if you may remember, n naught, this n naught was mu over u. So psi dagger 1 psi 1 is the first order correction to that. It's independent of u, but that's only because there was a 1 over u in here. But if you pull the 1 over u out front, then it becomes of order u. So it is a correction. And the reason we have that correction goes back to this. Okay, this not very clearly a visible term here, right? So there's this term here, a squared psi dagger psi. It comes from just taking a squared psi dagger psi. Now you just take the expectation value of psi dagger psi. That gives you n naught plus expectation value of psi of the. It counts all the bosons in the condensate and out of the condensate.
I see. Thank you.
Sure. Yes.
Actually, what I want to say is exactly what Patrick asked. Is just except that it looks the rho is in rho, the density seems like in the equation you write in the next page proportional to n0 squared instead of n0. But in the
I misspoke when I said n0 squared. They should just forget that statement. I misspoke.
In the top of the equation in that page, like you write n0 squared rho, you see the second line in the black. The second line in the you see.
Thank you, Juven. Thank you, Juven. That's a mistake. Thank you. Sorry about that. Let me erase that. So let me see if I remember how to do such a thing. Let's see.
N0 is the condensate for the density for the condensate.
Yes.
And then the additional contributions, it may not come from. What's
just 1 second? Sorry.
I think it's okay. You can just close it or something. It doesn't matter.
No, I will fix this. There we go. There. Okay, not a very good erase, but now I can put the black in there. There. Sorry, thank you for pointing that out. That should not be n0 squared.
Okay. What's the physical meaning for the second term, away from the n0, from the condensate density? Just make sure I understand that. Sorry.
This one?
Yes, the second term.
Yeah, so this is exactly the same as psi dagger 1, psi dagger 1. Same thing.
But what's the meaning for that?
Those are the bosons outside the condensate. So let's go back to the lecture on bosons. So, we did this computation way back when? Sorry. Yeah. So we computed B dagger K, BK. And so therefore we found B dagger K had this delta function at 0 momentum and this 1 over K decay. So what I'm computing now is the integral over this, all of this. This plus that. And and this is this function here. We computed these are the bosons outside the condensate. Sorry, this is the boson in the condensate. Those are the boson outside the condensate, and I just integrate over K.
Condensate, okay. Peak at a delta function. That's the condensate you are counting.
That's correct. That's the condensate.
Everything else is the additional contribution. That still contribute to the superfluid stiffness.
Correct. Yeah. So both this term and this term contribute to the stiffness.
No problem.
So that's the point. So naively, you might think this is what superfluidity is due to this. So this is the only thing that will appear in the stiffness. That's not correct. This also appears. And roughly the idea is that these excitations above the ground state, they are quantum coherent excitations. They're all also in phase with the condensate. It's because you haven't lost your phase rigidity. You just lost some bosons, but those bosons outside the condensate also remember the phase because when you did this Bogoliubov transformation, you mixed particles with holes, and when you're mixing them, there's a phase of the condensate comes in. This transformation here. So you're mixing, well, you have to take the inverse of this. Here. So you're mixing a particle with a hole, and in between them, the phase of the condensate comes in. So the particles outside the condensate are also phase coherent. These are not thermal excitations, which come in at random phase and give you noise. this is sort of a coherent quantum fluctuations, which doesn't destroy the phase of the condensate, and that's why it contributes to the superfluid stiffness.
Sabir, I have a question.
Sure.
So when you write a current at side side, I saw that this is automatically the total density of the superfluid. So where does the higher order corrections come from?
From this, there's a second order term over here, which I have dropped. Psi 1 dagger, psi 1, there'll be next order, there'll be another term here. Which I've, so let's see. So it's equal to this plus, there's another term here, which I didn't write down, something like psi 1 dagger, grad psi 1. That I can't drop because when I integrate by parts, I just goes back to this. It doesn't give me 0. Over here, because linear in psi 1, I can integrate by parts and give me 0.
I see.
So this term will give you higher order corrections.
I see.
Yeah, so the diamagnetic term is just the density, period. But there are corrections from the paramagnetic term at higher orders. If you don't have Galilean invariance, you need Galilean invariance to prove that these higher order terms all cancel.
Is it like some? So maybe in terms of diagram means that the anomalous dimensions of something is 0, something like that.
Yeah, no, but it really, by Galilean invariance, what I mean is that you really need the fact that this dispersion here is k squared. Okay, if this was anything else but k squared, then you'd get corrections. The fact that the dispersion here is just h bar squared k squared over 2m, that's important.
I see.
So that's not true for Cooper pair or anything else. So you do expect corrections, and you do get them. Sometimes they're quite large because you have a more complicated dispersion of the fermions or of the Cooper pairs than in helium-4. In helium-4, this is the dispersion. There's nothing else. So the argument is just perfectly okay.
I see.
Yeah, this is the term that implies Galilean invariance. Kinetic energy is 1/2 mv squared. You need that. That's Galileo's famous result. Well, he didn't phrase it that way. He didn't even know what energy was, but anyway. Other questions? Okay, so great. So we'll have a discussion session tomorrow morning at 9. I could, I don't know if you feel I should have some other time. I mean, there are people who show up and we have a great discussion that lasts almost an hour. But it tends to be the same group of people. If there are other people who feel that there's another time that might work, just send me an email. Or, and also free to, if you want to have an individual discussion session with me or how you just contact us on Slack or on email, and we'll be happy to set that up.
Last comment, if it's okay.
Go ahead, Julian.
I think here, mostly when we treat the gauge field, big A, electromagnetic gauge field, we basically treat it as a background gauge field. Even though in the real world, we have a dynamical gauge field.
Correct.
But in the vacuum of a true superconductivity, if we really care the true vacuum, I think the gauge field need to be dynamical. The U1 gauge field need to be dynamical. It will be spontaneous breaking to Z2 as you may discuss later. But somehow when we try to probe the theory as you are trying to do for the macroscopic theory, mostly we still did treat it as a background gauge field. That's the only comment I have.
Yeah, no, that's correct. So there's to get the dynamics of the gauge field, you have to put an E squared term in the Hamiltonian, which we're ignoring, because then E and B are conjugate, and then you have photons. So you have to couple this to actual photons.
Yeah.
So we are just taking the low frequency limit, where the London penetration depth was our non-relativistic limit of the of the Higgs mechanism, because the photon, I should say, if you take a relativistic version of this argument, I didn't, did I say that? Here, this field theorist would write this as del squared B is equal to m squared B, and there's the mass of your photon. Where this would be the Dahlan-Berchian or something, photon mass. So there's your Higgs mechanism right there. The equation of the Meissner effect, sorry, I should have mentioned this, thank you, is precisely the photon mass in a non-relativistic context. It's not a mass, it's an actual exponential decay of the field. But, photons at finite frequency, and then they become plasmons. So there, it's a little ambiguous whether you want to call that a mass or not, because in this case. But if you just did the naive relativistic generalization of that, that's the photon mass. Yeah, so that's one point. Second point is, once you have a gauge field, you don't have a global U1 symmetry, which I said was broken, was the fundamental characterization of this phase. What about the fact that the symmetry is not really broken? So what is the fundamental difference between a superconductor and a not superconductor? Once you include QED corrections. Well, there is a fundamental difference, and there it's even if you work in a compact gauge theory. So the Z2 mapping only works if the gauge theory is compact. This is if you have monopoles, but there are no monopoles. If there are any monopoles in the universe, they're very high energy. So that's not really. But you can imagine a Gedanken experiment where you put a monopole source by take two solenoids. So you imagine an experiment like this. Okay, so yeah, this is fun. So here's your lump of metal or superconductor or whatever it is, and then you come in and you have some solenoid, some external solenoid, which comes into the center and is this source of a B field that's going to spread everywhere. And you have another solenoid here, and goes this. So these are like, it's like a bar magnet, if you wish. Yeah, you can just put a bar magnet inside a superconductor if you wish. So there's a north pole and a south pole. So if this was metal, what will happen in a metal is that you'll get the usual dipolar field. So the magnetic flux would spread out this way. So that way. So this is the B field in a metal. So if you try to move these things apart, they'd be quite easy to move. It'll be some 1/r³ force or something between them. And so therefore these two monopoles, or the north and south pole of a magnet, if you try to separate them, they're deconfined. So monopoles are deconfined in a metal. They can just move them apart. But if this is a superconductor, then what will happen to the magnetic flux? Well, it'll form a thin tube. This is B in a superconductor because of the Meissner effect. It won't want to spread out. That costs too much energy. It'll form a thin tube. And if you try to move these apart, there'll be a linear force between them. So they'll be confined. So that's actually the fundamental difference in QED between a superconductor and a metal, whether the monopoles are free or confined. And as I'm sure you recognize, Juven, this is like the dual of the picture of what happens in QCD. In QCD, you have electric charges which are confined by a flux tube of electric flux. And that's the theory of confinement of quarks. And in a superconductor, you have confinement of monopoles because of expulsion of magnetic flux. And it's this. In fact, this was the inspiration, I think, for Tufte and Mandelstam and others, just for understanding quark confinement. It's kind of a dual, electromagnetic dual, where you interchange electric and magnetic fields when you go to QCD. Okay.
Very nice. I have one more, just to continue this comment, because Subir is going to visit the IS Princeton next term. Is that right?
Yeah. Yes.
So,
yes.
Because you are talking to Nati Cyber, and also a lot of students here, maybe some of you are already field theorists. So let me just clarify one thing. Nati Cyber will ask you whether field are dynamical or background field. And naive way, when Subir right, maybe he was just saying that we should just add the kinetic terms. Maybe like, you know, there's Maxwell F wage, F squared, or F mu nu, F wage star F, whatever. But that's not quite precise. Actually, the thing is that in the end, you should write down the full partition function, the path integral, and the question is dynamical or not. It's actually whether those gauge field, the configuration is summing over or not. And the previous question I was saying was just that inside the superconductor, I think the gauge field, the configuration should be summed. However, when we try to probe, and what Subir tried to do today, actually he tried to put a background field probe by the experimental frame. And that was the distinction. I try to say inside the superconductor, the true vacuum you are studying, you should sum in over the gauge configuration to really understand the theory. So the partition function, you should have a summation of all the gauge configuration. Well, outside, you try to fix some background. Yeah.
Oh,
that's it. Okay.
All right, Jivan. Thank you. Everything you said is correct. Let me quickly summarize. Yeah. If you think of the gauge field as just purely background, in other words, like physics term, if you ignore photons, then this characterization of a superconductor of off-diagonal long-range order is perfectly fine. But suppose you now really have full photons, full gauge fluctuations, then this quantity is totally meaningless because it's not even gauge invariant. So you can't possibly even do a thought experiment to measure this. So what I was mentioning that I can imagine a different thought experiment where I insert a bar magnet inside a superconductor or a metal. And imagine I have the freedom to move the north and south poles apart. Then the force the north and south poles will feel will tell me, that's the more fundamental characterization, which works even when the gauge field is fluctuating between a superconductor and a metal. But this is not an issue that has ever appeared in any condensed matter or ultra cold atom experiments. So this is purely for your entertainment. Maybe it will someday, you know, but okay. So I shouldn't be so dismissive. Well, but historically, it was this kind of thinking that, in fact, led to understanding of quark confinement as an electromagnetic do all of this.
I think even though the mathematics of that one, for the non-abelian one, is still not precise. So
yeah, okay. Understanding in quotes. Right, of course, we don't fully understand quark confinement. It's much too complicated. This is a baby version of it.
Thank you very much. Very nice.
Okay, any other questions from someone other than Juven? Thank you for your questions, though, Juven. Good questions. All right, so see you tomorrow then, I hope, or please let me know if you'd like to meet some other time. Okay, bye.
Thank you.